Hey everyone, this is Kanav again. I'm a final year 6th semester student from Computer Programming and Analysis, and today I'll be going over with you the Deep Learning Assignment 3 for Python. Let's get into it. So first of all, I would like to introduce you to the assignment. As you know, the assignment was given to us by our professor. It has two parts, part A and B. Part A and B, both of them are pre-coded, right? And we're supposed to answer some few questions. There are two questions for part A and around 8 questions for part 2. 10 questions, 5 marks, right? I hope this is pretty clear and we'll be moving forward on how these things are going to work. Assignment is easy, but it was a little time consuming. Well, why I said it was time consuming? It was a little trouble for me as I was not very familiar and I had to run. Um, like I didn't set the runtime. I didn't set the runtime as GPU, and it took like a lot of time, around 2 hours, to load my program. But here I am, and I'll be going over the program now. So the very first question said import the necessary packages, libraries. Right? We are going to the part A. In part A, we were supposed to begin with image convolution and then importing the image. We imported the image from the given code. As you know, all this code was given to us by a professor. So we get the image from the URL, we visualize the content for the response, right? And let's see what image it was. So we plot the image and we realize this picture is of a Lamborghini. Well, great choice, professor. Well, we had a picture of Lamborghini right here, and the code goes on where we print the array shape. We compare the values of color channels 0 and 1, and we compare the values of color channels 1 and 2. We get different answers, and we move forward with the code. Then the color channel 0 is saved in the input image array, and we print it. So what we do, whatever we got the result, we save it in the input image array, and then we plot it. So now you see it's basically the same picture, but the colors have turned, the colors have changed. Let's move forward with the code. So the next one is to visualize the values inside of the resulting array, right? So we just run the code input image array and we get all the values right there. Moving forward, now this is not part 2, this is still part A. We are going deep into part A to realize where things are gonna go, right? Now how convolution works. What is a convolution? We have a link here which we can always visit and check how things work, right? You see how every block is like further connected to 9 of each? How things work there? Perfect. Now let's get back. This is how convolution works. We are supposed to create a padded array by adding 2 rows and 2 columns, right? So we already have that array and we're creating like a padded array. We're adding 2 columns, 2 rows. We do that by the padded array command, np.pad. We create a kernel and we create an output filled with zeros with the same shape of input image. We compare both the arrays and we apply kernel to the array values. Then, when we plot it and we say the color gray, you see how the same picture went from this to this to this. Talking about the standard. So here we were just talking about what convolution is and how it works in 2D kernels, two-dimensional kernels. Let's talk about the standard convolution, right? Standard convolution define a function to squash out the values between 0 to 255 range. We run the program, we run the code was given to us. So all this code was given to us by our professor. We tried out standard convolution, we tried out line detection. Line detection, as you can see in the result itself, this is like you see how unique it is. It's like the outline of the card has been highlighted. So it's basically the color inside was taken out, and wherever it's like the two lines meet, wherever it's a boundary, wherever lines tend to shape an object, those are highlighted right here. Now, the questions. Questions for first part. First part asks, based on the kernels represented in the above image, create a kernel to detect 45-degree line using convolution and apply to the car's image. So whatever we did right here, using that we are supposed to create a new kernel. So I named it my kernel, right? So my kernel would be np.array, and what it says, we are supposed to detect 45-degree lines using convolution. So whatever lines are at 45 degrees, we are supposed to find that. So we use this transfer 45 degrees, we convert the 2D kernel and we compare it with our kernel, and there we get this. Moving on to the next question. Based on the kernels represented in the above image, create a kernel to detect 135-degree lines using convolution. So you see, it's pretty much the same what we did here. We did 45-degree lines here, and we are doing 135-degree lines here. These two were basically the same questions with just different values. So if you know how you work on this one shouldn't be hard, right? The code stays the same, right? I just changed the name from my kernel to my kernel 1, maybe like my kernel 2, like that, right? So we went from 45 degrees to 135 degrees. Moving forward to edge detection. No, hold on, not edge detection. I'm sorry. We are moving forward to the next question. Now we are applying the following kernels into your image to plot the output. These are the image made when we plotted our first kernel with a 45-degree, and these are the images made when we plotted our kernel with 135 degree. Next it says, I guess the question is, I'm not sure if I end up deleting this question by mistake. So we would just move forward to part B. In the part B, again, we are importing libraries, we are preparing some data sets. This is all pre-coded. We are just, like going through the code and how things are going to work. Let's go a little forward with how custom callback class for logging work, and then we train the network. As in the, like, even in the previous assignment, if you guys remember in the previous video I just posted, the training the network was like a very, very, very crucial part, right? So we have been training the network, we have been plotting the results, we have been seeing where things go. And after running all this long code for part B, we have 8 questions to look forward, right? Let's do them. Question number 3. Did the network present signs of overfitting? If so, which epoch? We do have overfitting in this model. The overfitting starts when the validation accuracy starts falling. However, training accuracy keeps increasing. From that point, we can see overfitting, right? Then write down how many layers this model has and identify their types. This model has 5 layers. Starts from a 2D convolution layer, a max pooling layer, a flattening layer, 2 dense layers, and a ReLU and a softmax. Then briefly explain what is the purpose of each of these layers. Well, that was a good question, right? So let me just get over that. Right, so the convolution layer contains a set of filters, parameters of which are to be learned throughout the training. The size of the filters is usually smaller than the actual image. After that, we have maximum pooling, and it's a pooling operation that calculates the maximum or the largest value in each patch of each map, and we move forward. We're supposed to add one more convolution layer to your model and run it again. We did that. This is how we do that. We compile a new model. We finished all the epoches. We call the result for plotting. We plot it. This is right. We have it right here. We have we have to compare the results. Upon comparing, we realize that the newer model we have is at a better accuracy compared to the first one, because latest one we have 2 convolution layers. Then we move to the 8th question, where we add a dropout layer to your model, run it, and compare the result with previous one. We add a dropout model right here. We compile it. Again, we finished all the epoches. We finished compiling. We compare it. We plot it, and we have another question coming up explained by what is the purpose of dropout layer and how it works. So if I say in a simple language, the dropout layer is to prevent neural networks from overfitting. And basically, it's going to avoid overfitting, right? The outputs of a layer under dropouts are randomly subslammed, right? And it has the effect of reducing the capacity of thinning the network during training. In testing, we can use this layer to reduce the model capacity so that our model can achieve lower generalization error. Moving on to the last question, make any other modifications in the hyperparameters and improve the model's accuracy and compare the final result with the previous one. Once again, we have to add another model, we have to compare the model, we have to compile the model. We plotted the model, and right there you see how we started with the very first graph right here. The validation accuracy and the training accuracy had a big difference. Meanwhile, we kept on going and running and compiling and plotting and testing, and we ended up with validation and training accuracy almost being the same. Right? This is what was all about um, this assignment. I hope you liked the video, and I'll see you next time.